Okay, so let's start. So far in week 1 to 3, we have seen different things. We have seen how do we capture the underlying meaning of data by PCA, kernel PCA, then clustering. In week 4, we'll be looking at what is the probability distribution from where our data is getting generated. So whatever is our data, it comes from some probability distribution. Okay. And our goal here is to find the parameter of the probability distribution from where our data is coming. So is that clear? Hello? Am I audible? Yeah. Am I audible?
Yes, yes, you are audible.
Okay. So in this week, we'll be looking at estimation. And we assume that the data we have, there is some probabilistic distribution that generates the data. So our goal here is to find the unknown parameter of probability distribution from where our data is getting generated. And there are few steps involved here. So step one is we observe the data, what type of data we have. After that, we assume a probabilistic model. That is, we assume a probability distribution from where our data is getting generated. And after that, we find the unknown parameter of this probabilistic model or probability distribution. So these are the steps involved here. So let's take one simple example. Let's say we have data and in data we only have ones and zeros, so our observation is 1011 011, something like that. Okay, all other values are 1. So this is our data. Now, well, as the data has only ones and zeros, so we can say that okay, this data is coming from uh, it's coming from tossing a coin where 1 corresponds to head and 0 corresponds to tails, right? We can say that. So now, so what we have concluded from this, from the type of data we have, as we only have zeros and ones in data, we can say data is coming from flipping a coin. Okay. Well, now what's the second step? So by that I mean, what's the third step? So for the first step is to observe the data. After that, based on the data, we have a probabilistic model, and here the probabilistic model is flipping coin. The data is coming from experiment of flipping a coin, and after that, we want to estimate the unknown parameter of generating this data. Where in this case, it is finding the value of p for the coin, finding the value of unknown p. Okay, this is what? This is unknown parameter. Is that clear? Hello. So is this setup clear to you all? Any problem? Okay, let's continue. So now, well, how do we find a good guess for P? Well, mm, this data, this can come from any value of P between 0 and 1, right? This data can be generated from P is equal to 0.0001. Well, this can happen, but it's very unlikely, but it is possible. And also this can come from P is equal to 0.9. Okay, so here here P belongs to interval, well, 0 and 1 won't be included. It belongs to interval 0 1, where endpoints are not included. So now the question is, what is a good guess for P? So for finding that, we have few assumptions. First of all, so assumptions. The first assumption is of independence. What do we mean by that? When we say that your jth toss resulted in heads or tails, that will not change the probability of outcome of ith toss. That is what we mean by independence. Outcome of one flip will not influence the outcome of other flips. As simple as that. So mathematically, probability of xi given xj will be equal to probability of xi, because probability of xj is not affecting probability of xi, and this is true all for all I not equal to j. This is the first assumption. The second assumption is of identically identical distribution. Well, what do we mean by that? This means that all these zeros and ones, they are coming from flipping the same coin. We are in all these flips, we are using the same coin. That is, the value of P is constant. So this is what we mean by identically distributed. Identical distribution. So mathematically, probability of xi equal to 1 is equal to probability of xj equal to 1, and it is equal to some p that we don't know for all ij. So these are the two assumptions we have to make before jumping on what's a what's a good choice of p. Okay, so any doubts so far? Hello. Okay, let's go ahead. So now, well, uh, now the question is, how do we find the value of p which is best in a way? So for that, we'll be using likelihood function. So let's talk about likelihood function now. Likelihood function. So, well, for this observation, some values of p will be better than other values, right? So when we plot graph of, just a second, yes. Well, let us plot graph of different value of p against probability of that p generating the data. Okay, so on the x-axis we'll have different values of p. So p is from 0 to 1. Okay, and on the y-axis we have what? Let's say for now our observation only has like four values, right? First is 1, second is 0, third is 1, and fourth is 1. So this is our observation. So the y-axis will be probability of generating this data, that is x1 equal to 1, x2 equal to 0, x3 equal to 1, x4 equal to 1. Now, for different values of p, the probability of this data getting generated will be different. Well, when p is equal to 0, this data cannot be generated, same when p is equal to 1. And for this observation, the graph will be somewhat like this, roughly. Okay, let me give it another try of trying. And here we want to find this peak value. What value of p will have highest probability of generating this data? What value of p is most likely to generate this data we want to find? So here for this, what we'll be using, we'll be using maximum likelihood estimation. So maximum likelihood. Well, first of all, we have to understand what is maximum, what is likelihood function. So likelihood function takes in takes in your candidate parameter for p. Well, this is the p, and it also takes the observation. So it will take your set of observation. Sorry, and this will give you the probability that this data, this observation that you have, this is generated when the value of unknown parameter is this. So this is equal to probability of generating this data when your unknown parameter is p. Well, when as the assumption is of independence, it means that this joint probability can be written as product of marginal. So this will be equal to probability of x1 being generated when your candidate parameter is this p, and same for all other values. And this we have done using the assumption of independence. So now this is equal to product over I from 1 to n of p raised to the power xi into 1 minus p raised to the power 1 minus xi. Well, this is a different way of writing Bernoulli distribution, uh, PMF. You can decode this. If your xi is equal to 1, in that case, this entire thing will be just p. And when your xi is equal to 0, this entire thing will just be 1 minus p. That you can check. So now we want to maximize this value. That's our goal. So any doubt so far? Anyone? Hello. Is everything clear? Any doubt so far? Yes, no. Okay, let's go ahead. Now, this was about likelihood function. Now we want to maximize this. So first of all, before that, we can simplify it again, right? Simplify it. So now just look at this term first of all. This p raised to the power xi is getting multiplied n times, right? So first of all, you have p raised to the power x1, then into p raised to the power x2, up to p raised to the power xn. So when this term is getting multiplied n times, so base is same. So we'll add the power. So this will be equal to p raised to the power x1 plus x2 up sum up to xn. So simply summation I from 1 to n, or simply I'm just writing it as Sn denoting the sum of xi's. And here for the other term 1 minus p raised to power 1 minus xi, when this term is getting multiplied n times, so what you have base is same, so the power gets added. So when your 1 gets added n times, so it will be 1 minus p raised to the power n. And when your xi gets added, it is Sn, as we have done here. So this will be n minus Sn. Yes. So now we just have to maximize this. So we want to find p hat maximum likelihood, which is equal to the value of p that maximizes the likelihood function. So now, as here we have a lot of things in power, so to deal with this, we can take log on both sides. So on taking log, sorry, this will be equal to argmax of log of the entire thing. So log of p raised to the power Sn into 1 minus p raised to the power n minus Sn. And now just use the property of log. So this will be equal to argmax of, sorry, well, this will be log of p raised to the power Sn, and this Sn will come here, And for the other term, we'll have n minus Sn, and here we have log of 1 minus p. Now we just have to find the value of p. So what we'll do, we will differentiate this with respect to p and equate it to 0. So differentiate with respect to p and equate it to 0. So on differentiating with respect to p, what we get? We get Sn by t plus, here what we'll have? Here we'll have minus of n minus Sn by 1 minus p equated to 0. Then this implies that we'll move this term on the right side. This is Sn by p equal to n minus Sn by 1 minus p. And further simplified, so this is Sn minus, second, yes, Sn minus, is there anything wrong here? Yeah, any doubt so far? In the meantime, I'll just cross check this. Hello, any doubt so far? Hello, am I audible? Okay, let's continue. Okay, well, what we did here, we simply differentiated this with respect to p. So log p, this is a constant, and differentiation of log p will be simply 1 by p. Then we differentiated this thing, this is a constant, so it stays here. Then differentiate this. So differentiation of this will be what? It will be 1 by 1 minus p, and differentiation of this thing will be minus 1. So this we have here, correct? Then we just have to simplify it further. So this will be Sn into Sn into p, and here it will be n into p minus Sn into p. Okay, so these two things will get cancelled, and now here your p hat is equal to what? This is Sn by n. Sn by n. And what is Sn? It is simply sum of your xi from I equal to 1 to n. So what is your p hat here? It is simply average of xi's. Yes. So in case of, in case when your way of generating data is flipping coin, that is when your data is coming from Bernoulli distribution and you want to find the value of unknown p, simply the best guess for p will be average of all the xi's value, and as all the values are just zeros and ones, this is nothing but number of ones you have in the data. Yes, so is this clear? Hello. Okay, so now from here we can develop, we can understand one approach, right? So the first approach is observe the data, and depending upon the data, you choose your probabilistic model. You choose your probability distribution from where your data is getting generated. Once you do that, after that, you just have to use maximum likelihood approach, find the value of a likelihood function, differentiate it, equate it to zero, and find the value of unknown parameter. So let's look at different example. Okay, let's look at condition where the data is not just zeros and ones. When the data belongs to R, how things will be different in that case. So what's the other example? Well, our data has some values and they belong to R for all values you have in the data, for all i's. So what now? So the first thing we have to do is look at the data. Well, the data is such that all values belong to R, and based on this we have to choose our probabilistic model, that is our probability distribution, which generates this data. So what's a good probability distribution generating data belonging to R? Anyone? Hello? What probabilistic model we can assume here? Hello, am I audible? Yeah, I would really appreciate if you guys unmute and interact. Hello, are you guys there? Okay, yes, as someone said in the chat, we can assume here that the data is getting generated from Gaussian distribution. It is normal distribution or bell curve distribution. So now here your xi's are coming from a Gaussian distribution with mean mu, which is unknown, and we'll assume that variance is known. So, well, here you have Gaussian distribution generating data. Leave this. So now what? We assume that okay, your unknown mean mu is unknown and your variance is known. So what's the first step now after this? Find the value of your likelihood function. So your likelihood function takes in the parameters, candidate parameters, mu and sigma square, and it also has your data. So now here we don't have to, well, here we can't find the probability. Well, because these values are belonging to continuous distribution, right? They come from a continuous distribution, not a discrete distribution. So here we have to transition to probability density function. So, well, the likelihood function here will be equal to the probability density of this data being generated when these are the value of unknown parameter. So the data is x1, x2 up to xn, and the unknown parameters we have is mu, and the known one is sigma square. That is variance. Now simply, well, as these are independent, as xi's are independent, this is nothing but product over I from 1 to n fxi, taking some value small xi, when your candidate parameters are mu and sigma square. Sorry. Now, what's the next step? Simply put the value in your PDF. Okay, and let's look at the PDF of Gaussian. If you guys remember, the PDF is what? So summation, sorry, product from I to I equal to 1 to n of 1 by root 2 pi sigma e raised to the power minus xi minus mu whole square divided by 2 sigma square. This is the PDF. Okay, and we are multiplying the same thing again and again for n times. So what will happen to constant terms? They will be simply raised to the power n. Okay, so let's look, as we discussed here, what happened when we multiply each term n time. We'll discuss the same thing here to simplify it. So now this will be equal to 1 by root 2 sigma, sorry, 1 by root 2 pi sigma, this whole thing raised to the power n, and this e raised to the power, this entire thing is getting multiplied n time. So the base is same, so power gets added. So this will be e raised to the power minus summation I from 1 to n xi minus mu whole square divided by square. And as it's a constant, this numerator, we can take this out. And what's the step after this? As we will simply differentiate this and equate it to zeros, so the constant terms will not matter. So the only thing that will matter is this part, e raised to the power summation of this entire thing. So the only relevant part here is sum. Okay, I'll just write it. So the unknown mu, the mu hat we get from maximum likelihood will be nothing but argmax of the argument that maximizes this summation I from 1 to n minus of xi minus mu whole square. And this, how we get this? Well, after this, what you do, you take the log. So on taking the log, and just ignore the constant terms, ignore this term and this term, and when we take the log, what will happen? This entire thing will come in front, and as you have e here, this will vanish to 1. So you simply have this term here. That's it. And now we just have to differentiate it and put it equal to 1. Do you guys think you can do that on your own, or do you guys want me to show the simplification entirely? Anyone? Hello? Hello? Am I audible? Are you guys able to understand this part, or do you guys want me to show the entire simplification? Okay. Looks like you guys are able to understand it. Okay. So the value of mu that we will get from here is mu hat ml will be equal to 1 by n summation I from 1 to 1 of xi. Well, here also the value of unknown parameter is average of xi's, but this will not happen in case of all the distribution. Let's say if you have taken your probabilistic model to be Poisson distribution or geometric distribution, this will come out to be something else. So is the approach of maximum likelihood clear to you all? First of all, what we do, we observe our data, and depending upon what kind of data we have, what's the problem statement, we choose our probabilistic model, that is probability distribution from where your data is getting generated. After that, you simply find the value of unknown parameters that maximizes the likelihood function. So is this clear to you all? So after this, we have to move to uh, other method of estimation. So this was the first part of estimation using likelihood function. The other part is Bayesian modeling. So when do we use Bayesian modeling? Is there something anyone wants to add or ask? So now we are coming on Bayesian modeling. So let's say we have data of all zeros and ones. It is coming from, as we assume that it comes from Bernoulli distribution. It comes from flipping a coin. Okay, and let's take a simple example. Let's say you have a coin. You want to find the value of p for that coin. Well, sometimes what happens, let's say your coin has a bend. So you think it's more likely that the value of p for this coin will be what? Close to 0 or close to 1. That's more likely. So that's your prior belief depending upon the coin you have. That's the belief you have because of the bend in coin. So now somehow we want to incorporate this belief system into our estimation. So here comes your Bayesian estimation. Okay. So is the approach, is the reason why we use Bayesian modeling, is that clear? To incorporate our prior belief about the generation of data into estimation. Is that clear? Okay, great. So now what we have to do here. So, well, we believe we believe that P of coin close to somewhere close to 0 or 1 because of bend in coin. So, how can we incorporate this belief about your parameter into estimation procedure? That's the question. So, well, what we said, the value of p is somewhere close to 0 or 1. So, because of this, we can say, well, we believe that the p here, yes, and one important thing that I forgot to mention that in Bayesian modeling, the p, the unknown parameter, is considered to be random variable, whereas in likelihood estimation, it is considered to be a constant. Yes, so as we are considering our unknown parameter to be random variable, it can have distribution. And based upon our prior belief, we can give it different distribution. So this prior belief that the value is close to 0 or close to 1, this can be converted into distribution. And the distribution will look somewhat like this. It will be okay, like this. Yes. Now, this is 0, this is 1, and we say that it is somewhere close to 0 or 1. So the probability density function for our unknown p will be like this, roughly like this. When well, for value of p close to 0, we have high uh, probability, whereas for other values, you have lesser probability compared to when you have value of p close to 0 or 1. So this is our prior belief about the distribution of p. And after seeing the data, this may change. So this is our uh, approach here. We think of parameter of estimation as a random variable based on our prior belief that the unknown p will have some distribution, and after seeing the data, that distribution may change. Yes, so is the idea of Bayesian estimation clear? How do we approach problems here? Hello. So we have this belief system, belief about the unknown parameter, or you can say hunch. we have this hunch about the uh, unknown parameter, we we use probability distribution for for framing our belief into mathematical model. And it has some distribution over a known parameter. Let's say parameter is theta. Okay, so your prior distribution of theta you'll have. Okay, this is called prior. After seeing the data, this prior may change, and that is the distribution of, well, it is distribution of theta after seeing data, and this is called posterior density. Okay, so this is a framework we have in Bayesian estimation. And what do we use here? How do we incorporate this data into our prior density function? For that, we use Bayes rule. So Bayes rule for that. And what is Bayes rule, if you remember? So the probability of A given B is equal to probability of B given A into probability of A divided by probability of B. Well, in parametric estimation, how this can be used in Bayesian parametric estimation. So let's say we have parameter theta. Well, A here, A is what? A is the unknown parameters you have. Thetas you have, and B is what? B is your data. Now, the probability density of your theta given your data, this you have to find. This is your posterior. And your posterior will be equal to what? Will be equal to probability of getting this data when the parameter is theta. So this is what? This is probability of getting this data when your unknown parameter is theta. And what is this? This is your likelihood. This is your likelihood. And multiplied with probability of getting this theta. And this is what? This is your prior. And this entire thing is getting divided by probability of this data. Well, and this thing does not depend on theta. So when we can remove the denominator, and this will be what? Posterior will be directly proportional to what? This is your likelihood, and this is your prior. So from here, what we get? From here, we get the proportionality equation that posterior is directly proportional to likelihood into prior. So, for example, what this will do to our parameter distribution of our unknown parameter. So, let's say our belief was that the value of p is close to 0.9. So, just a second. So, density, the probability density for p is somewhat like this. And after seeing the data, well, the data we have is this. It has a lot of zeros and few ones. So this is contradictory to our prior belief. So it will significantly change our posterior. The posterior we'll have will be very different from our prior. Now our posterior will be, let's say, it will be, sorry, it will be something like this. So depending upon the data, our posterior may change, or uh, depending upon the data we have, your posterior may change from your prior, or it may strengthen the prior belief. So in other case, when your data has lots of ones and very few zeros, let's say this is your data. So in this case, your prior belief will get strengthened. So this is what happens in your Bayesian estimation. Okay. So far, any doubt? Hello? Yes. Okay, let's move ahead and let's talk about this a little more. So now let's talk about what can be a good prior. Well, here you just we had this random graph of prior. So when we are dealing with Bernoulli distribution, and when we want to find uh, the unknown parameter using Bayesian estimation, then a good prior will be your beta distribution. And why? Let's talk about that. Good prior. When your data is just zeros and ones, that is when it is coming from Bernoulli distribution. So a good prior will be beta distribution. And why is that? Because beta distribution has uh, two unknown parameters, al- alpha and beta, and using by tweaking the two parameters you can get any type of graph. And the important thing why we are choosing beta distribution is that the beta distribution is between 0 and 1 only. So your beta prior, and its PDF is given by this. So this is your beta prior. So now let's look at the Bayesian estimation again using this beta prior. Okay. So here you have to find the probability of theta given the data. Okay. And it is directly proportional to what? Your likelihood into prior. And what is your likelihood? Likelihood of seeing the data given this value of theta. And what is your prior? Prior is your density of theta that you have taken as prior. So from here, your posterior density of theta given the data, this is what? Directly proportional to your likelihood. And what is your likelihood? This we have just done few minutes ago. This product over I from 1 to n of p raised to the power xi into 1 minus p raised to the power 1 minus xi. This is your likelihood. And your prior is what? You have taken beta prior. And beta prior is p raised to the power alpha minus 1 into 1 minus p raised to the power beta minus 1. So this is your likelihood. This is your prior. So on simplification, well, we have already done this. Okay. We'll just simplify this. And in the end, what you'll get? Your posterior density for theta. This will be directly proportional to p raised to the power summation over xi plus alpha minus 1 from here, and 1 minus p raised to the power summation over 1 minus xi plus beta minus 1. Well, this is of same functional form, right? This is also a beta distribution. So same functional form as your prior. This means that your beta prior with your data for Bernoulli distribution, for your Bernoulli distribution, the posterior density it gives is also a beta distribution. So it is beta posterior, and the parameters here will be alpha plus nh, beta plus nt. Yes. So this is one important takeaway from here. So now as you have your posterior density, so as taken up, as shown above here, this is the final thing you are getting after seeing the data, this, or it can be something like this, depending upon the exact values. So after you get the posterior density, you can do multiple things to find the value of P from here. You can take expected value of the distribution, that is mean of the beta distribution, which is what, when your parameters are alpha and beta, which is uh, in that case it will be alpha by alpha plus beta. You can take mean, mode, or anything else depending upon what you want. So once you have your posterior density, to find the value of P, you can uh, approach in different ways. So that was it for Bayesian estimation. So is that clear? Hello? Hello? Yeah. Any doubt so far in what we have covered? Hello? Okay, great. Yeah, so we have covered the estimation part mostly. In week 4, we have covered likelihood function and Bayesian modeling. Now we are left with GMM, Gaussian mixture model, and EM algorithm. That will take in tomorrow's session. Is that clear to you all? Hello.
Yes, sir.
Any doubts?
Sir, please tell the homework that what should we do.
Okay, yeah. Just go through the slides once. Lecture slides. That would be more than enough. Once we are done with week 4, we'll do PYQs. Yeah, next Wednesday we'll have session of PYQ. Yeah, thanks for joining. Let's meet again tomorrow.